Mine.
I think it has, yes. So go ahead.
All right. Thank you, Wouter. I'll start a timer in the meantime. I'll be giving a talk about what I've done last year under supervision of Kees, and Shuai Cheng was also in the audience, and a colleague of theirs called Lech Grzelak, who works at Rabobank, who knows what's really going on in finance, as he works as a quant over there. And yeah, so I did that before I started as a PhD in December at the CWI. And what I was looking into is see if you can use neural networks to generate financial asset paths. So that could be useful in the context of Monte Carlo simulation, that you could very cheaply generate a data set at large time steps to price certain options. For example, last week we saw Boris's nice presentation about a model for electricity prices, right? So if you take models and you don't have as nice a technique as Boris does, then you may want to use a Monte Carlo simulation, but you may not be interested in all the intermediate steps. So we were looking if you can sample these asset processes with neural networks, and one particular neural network called a GAN. So that's what I'll be talking about today. And the specific focus is on strong solutions. So that's something that sets it apart from other literature where you just have a data set and you try and generate what's in that data set. So let me give you an outline. So first I'll give you some background on stochastic differential equations and our problem setting. Then I'll show you the algorithm, the GAN, what it is, what it does, and why we use it. Then I'll show you how I'm generating these paths, and I'll give you a brief overview of some key results. I won't show everything, but some key highlights, and then we'll go on to the usual discussion and conclusions. So as a refresher, what are SDEs? So suppose we have some probability space, then an SDE is defined as in equation 1. So we have some stochastic process that starts at a time 0 at an S0. And it's completely defined by a Brownian motion, WT, adapted to a filtration based on that Brownian motion. So in general, SDEs very quickly become complicated enough that there's no closed form solution available. So we need a numerical approximation. For that, you could, for example, use your discrete time scheme. So your cookie cutter discrete time scheme would be the Euler scheme, which you all know. So basically, if we write the SDE in its integral form in equation 2, then you see that if we take a stochastic Taylor expansion of that equation and we truncate at some point, depending on how accurate you want that scheme to be, you can truncate at certain orders, and then you arrive at a discrete version, a discrete time scheme version of that stochastic integral, as you see in equation 3. And I see in equation 3, I've just shown the Euler scheme. But you could also suppose that you know the conditional distribution of your process. Then instead of defining a mesh and then performing this discrete time approximation, you could also just sample from that conditional distribution. So I've written that here in equation 4. And for Ito SDEs, that's always possible because they satisfy the Markov property. So if you know the previous value, then you can sample the next value given the previous value with the conditional distribution. So these are ways in which you can arrive at a solution, at least construct a data set.
So Jorino, I cannot see your screen. Probably it's only me, right?
Is that true? Can other people see my screen? Or
I can see your screen.
I can see it.
Yeah, okay, so I don't know. No.
I can send you the presentation, Benjamin. Maybe that's, is that a quick fix that we can do?
Oh, sure, yeah.
Let me just
some setting that's wrong here.
No, but I can send you the presentation so you can just and then you can guess where we are in the presentation.
Yeah, sure. Thanks.
Okay. So
sorry.
No worries. So yeah, so if we look here, then basically what we're trying to do is all summarize into one picture on slide 5. So basically what we do is, suppose we have some kind of information up to time t, then we are interested in building a data set, in constructing a data set at time t plus delta t. So we want to know the solution at time t plus delta t. So you could construct, for example, normally the blue lines with a Monte Carlo simulation. So you could use an Euler scheme to generate the blue lines. But what we want to do is we want to get to time t plus delta t in a single step, or in just a few steps. And then we will do that with a neural network. So large here means large, a time step large compared to a time step you would typically need to provide an accurate discrete time approximation. And let's see. So yeah, I've tested this this setup on 2 relatively straightforward SDEs, but that are sort of rich enough so that we can still discuss some properties. Geometric Brownian motion, or GBM, and the CIR process. And probably you've seen GBM before, but the CIR process may not be very well known. So the CIR process is a model for interest rates. And it looks as in equation 5, that's the SDE formulation. And it turns out that the CIR process follows the non-central chi-square distribution. So this is an example where we know the conditional distribution of the next value given the previous value. And the non-central chi-square distribution has this property that, so it has this degrees of freedom parameter. So I'm calling it delta here. And if the degrees of freedom parameter is below 2, then it develops this near singular behavior near the origin when viewing from positive infinity. So I've plotted that on the right. And in the case where the degrees of freedom parameter is greater than or equal to 2, then it looks much less dangerous as the other distribution. So you have these 2 regimes where the distribution looks very differently. So this is a more challenging case than just the log normal distribution that you get out for geometric Brownian motion. So there's basically 3 regimes that we'll now be looking at. So the one for geometric Brownian motion, just try and fit the log normal distribution. This case where the degrees of freedom parameter is large enough, and the case where we have this an almost singularity around the origin. And in all these cases, we want the neural network to approximate the asset process. So there's one more thing that we need to understand about SDEs, and that's normally for an ODE. If you satisfy your initial condition and you satisfy the dynamics, then you have enough information, you've solved the problem. But for an SDE, everything is stochastic. So we're not just there yet if we only consider the dynamics themselves. So in an SDE, you distinguish between weak and strong solutions. So a solution is always a pair, a Brownian motion, and an asset process that satisfies the SDE. But a strong solution, if it exists, not every SDE has a strong solution, but let's assume it exists, then there is a unique relation between the Brownian motion and the process. So if you give me a Brownian motion realization, I get one of the blue lines, essentially, that you see in the figure. And there can be only one of those blue lines if you give me a realization of the Brownian motion. So in other words, almost surely the asset process you find that is a solution based on that Brownian motion must be equal. So that's what I've written under the bullet, like almost sure equality, and that's called pathwise uniqueness. So for every path and a Brownian motion pair, there is a unique process solution. But you can also define a different kind of solution. That's suppose that you found a process that satisfies the SDE, but is only at time t is only equal in distribution. It could even be defined on a completely different probability space, but it's still equal in distribution. Then that is called a weak solution. So for our problem, if you look in the picture above, that means that if we are interested in the exact value of the blue lines, if the blue lines are the exact solution, the strong solution, then we should look point by point at t plus delta t if our solution approximated with a neural network matches that process. But if we're only interested in a weak solution, all we have to do is match the distribution at time t plus delta t. So that's the two different features of SDEs that we'll be looking into. And the first thing, so basically I've been looking into three things in my thesis. The first was, can we just fit the distribution? Because that's basically problem number 0, almost. Can a GAN do what it's supposed to do, which is find a distribution at time t plus delta t. But then you would only be able to do that for a certain starting point and a certain delta t. And what we want to do is, start anywhere. So anywhere on the in the figure at the top, anywhere at any previous value S0 or ST, and then be able to look any time step delta t ahead in the future. So that would mean that the neural network would have to learn not only what the distribution is, but also how it depends on delta t and on the previous value. And that is something that is a slightly more challenging version, but that only relates to the distribution. The last question was, okay, what if we made that all work? Then does that mean we can also use a neural network to find a strong solution? So that's basically the things, the outline of what I've been looking into. So let's look at what a GAN is. So GAN stands for Generative Adversarial Network. And in machine learning terms, they're already ancient because it's from 2014. In the real world terms, they're quite young, so only 7 years ago. And they've been able to, they've shown very successful results when generating images. So I've given an example on the right. You see a lady that's been generated. This person does not exist. You may have seen images like this before, just completely sampled from noise and through a very large, absurdly large neural network by NVIDIA or similar companies. They have the resources to generate these things, but it's very impressive. And you can understand this as a very complicated joint probability distribution of pixels. But people have also been using GANs for time series and PDE solving, and many more applications. So this sort of inspired us to say, okay, can we use this as well? So the focus area has been this specific algorithm. And this is how they work. So I've made a schematic here. So the word adversarial in these networks comes from the fact that there's actually two neural networks in a GAN. So the blue neural network is called the generator, G, and that network continuously generates new suggestions of the solution. So it tries to approximate the data set. And the other neural network, it's called the discriminator, D. It is basically a classifier, a soft classifier that gives a score between 0 and 1 about whether it thinks that a sample it receives belongs to the data set, so the true data set, or whether it came from the generator. So it is trained by alternatingly giving it samples from the generator and giving it samples from the real data set X. And a score close to 0 means that the more that it thinks that the value was fake, so from the generator, and closer to 1 means that it thinks that it is coming from the real data set. And if it's near 1/2, so if it's in the middle, then it's not sure. Then it's basically flipping a coin. I'm anthropomorphizing a little bit, but that's the basic idea. So that is the idea in words, but how can we actually make that work? So there's some nice theoretical results you can make about GANs as well. I won't go into detail about that, but I'll just give you the Minimax formulation. So you can think about, again, about these neural networks as two players playing a game theoretic game together in an adversarial sense. So you can formulate this as a sort of Minimax problem. So to see this, for example, let's evaluate this. Let's look at the first term. Then what that first term is saying is that the discriminator is trying to maximize its score on real samples. And that makes sense because it's trying to classify correctly that when a sample came from the real data set. And the second term is being maximized by the discriminator as well. So 1 minus D means that it's minimizing its score on fake samples. That is also in line with what I just told you about the algorithm. And at the same time, the discriminator, or the generator, is trying to minimize the second expression. So it's trying to maximize the discriminator's score on a generated sample. It's trying to maximize D on G. So it's trying to fool the discriminator. And if you evaluate this function, you can cast this value function into a loss function, and then the learning problem is completely defined. So you can actually show that solving this problem coincides with equality in distribution of your generated data set and the real data set. And that's quite interesting, that from this very interesting idea, you can actually get to a result like this. And then D and G are implemented using neural networks, but in theory, they could also be, I don't know, quantum computers or something. The algorithm doesn't even depend on machine learning, on neural networks. So that's the GAN. And the GAN will be used as our tool to approximate that conditional distribution. So we have our tool to do that now. And we can use a slight modification of a GAN, of a standard GAN, that also takes as input the delta t and the previous value that we're starting at, so where all the blue lines in the figure are starting from. It also takes that as parameters. So it learns how the conditional distribution depends on those parameters. And there's some literature on people trying to do that with various applications, also financial time series. So that was the inspiration to use this setup. So we have a tool to do that. But what's still open is how do we get a strong approximation? Because GANs only can find the distribution. Or basically at the start, we didn't know, right? If we find the distribution, then does that mean that the GAN also finds a strong approximation? That was still open. So we needed a way to ensure that the GAN can also find the strong approximation. So in this figure, I've just drawn one of these lines because now we're interested, if we start at the first red dot at time t, we're not just interested in the distribution at time t plus delta t, but we want to get exactly that second red dot if we start from the previous red dot, given that event in the event space. So if we draw an exact sample with exact simulation, we want the GAN to also find the same sample, almost surely under the measure P. So how does that even work with exact simulation? Right? So the basic idea was to use a new type of GAN that does the same thing as exact simulation, but then by learning it. So in exact simulation, you can always view sampling from a distribution as I've written here. So you could say it's some inverse function, inverse distribution, if that can be defined, of course, but this is just a CDF that F stands for. So it exists, and the prior is just the normal distribution. And then we can always write the sampling of the next value S as sampling from just sampling a standard normal random variable and then applying that inverse distribution. And that's exactly what the stochastic collocation method tries to do. So normally, of course, you don't know that inverse distribution. That may be very, very complicated, but you can find it maybe empirically, or you can fit a polynomial expansion of Z of the standard normal random variables, which is called stochastic collocation, right? Or a similar technique, polynomial chaos expansion. To evaluate the conditional distribution. And the idea basically behind the what I call the constrained GAN, that's been a working name that I'm still using. The constrained GAN is to not use a polynomial approximation, but to use a neural network approximation based on that same Z. So why is that important? Because all the randomness in the process is captured in this Z. So if you think about the filtration that corresponds to an asset path, then once we sample an event, then the path will be completely defined. Like I said before, if you give me a realization of a Brownian motion, then the path will be completely defined by just integrating it over the in the Ito SDE. So that means that once we find a sample Z, then there should also be a unique S. And that's what we can see in the top equation from exact simulation. So replicating that property should be enough to get the strong convergence, or the strong solution, to find the strong solution. So how do we actually make that work for a GAN? Then we need some kind of training set. So we have to be careful about what the input and output is to the neural network. So like I said, it may be difficult to know the inverse distribution of that conditional distribution. So but we actually don't need that. All we need to do is to construct a data set. But we always do know the prior. So we can always cheaply compute the inverse of the normal distribution and then evaluate that on the conditional CDF. And then we also find the corresponding sample Z by bijective nature of the CDFs. So then the only challenge is how to set up the GAN. And what the architecture here does in the schematic is that instead of just letting the discriminator take the value from the generator, it actually now also observes the value Z that the generator got as input. And it also always receives the Z that is used to generate the training set. And in that way, it learns information not just about the distribution, not just about ST given the previous value, but it also learns information about how it should map to the next value. So how it depends on this Z. And if we do that, we basically constrain which outputs by the generator are allowed that correspond to the right points and which ones are not. And the standard architecture we'll call the vanilla GAN. So basically that acts as a baseline throughout the results. So let's see what this can do. I'll mainly focus on paths. So, but I'll quickly show just what happens if we try and fit the conditional distribution. So I've trained the GAN on 100,000 examples of these conditional samples with different ST and different delta T. So I've defined a range of these parameters that could vary independently. And then what you see here is I fixed the conditional parameter ST at 0.1, and I varied delta T for 4 different examples. And you see that in both cases, the neural network can actually adapt its output, so on its output distribution according to what the exact distribution should be. So it becomes sensitive to its input parameter, delta T. And this is a result if the Feller condition was violated. So if that delta parameter that I showed was the most difficult case, you see that in the red line, it gives this sudden dip to 0. So that's that near singularity around 0 that you see. But we can see now on with the naked eye that the vanilla GAN provides a less accurate approximation than the constrained GAN. And we actually saw in all the results that the constrained GAN also did a better job in approximating the distribution. So informing with this map from the prior to output actually also improved the weak convergence, the convergence in distribution of the GAN as well. So this is, now I'm just telling you this, but in my work also computed some statistics on that, but right now it's more interesting, I think, to focus on which paths we can generate with that. So now that we can generate the conditional distribution, how can we use that to construct paths? Well, we can basically iteratively sample from that conditional distribution. So say that we start at a value S0, then we plug that into our GAN, our conditional GAN, and then we repeat that process. So you see that here in the schematic that I've drawn. So every time we repeat the GAN on its previous output, and then that way we construct a discrete version of a path. And the black line would then be some exact solution, some strong solution to the SDE. So to construct an experiment, we'll partition a time interval into n steps so that we get different delta t's. And the smallest delta t is where n is 40 steps. So we cross the interval in 40 steps. And the largest time step is just crossing the entire interval in a single GAN step. And then ideally, of course, that the GAN shouldn't depend on delta t because it should always fit the right distribution regardless of delta t. But we'll see in a moment that that did not happen exactly. If we also have to use a trick to compare a path realization to in all three methods that I'm considering. So we need some kind of reference. I'll use the Euler scheme as a reference and the exact simulation schemes. But for that, we have to use exactly the same random numbers to generate the path. Otherwise, we cannot compare them point-wise, if you will. And we'll compute at every point the weak error, so the difference in the means, and we'll also compare the strong error, which is the mean point-wise difference in the path. So this is an example of what that looks like for the CIR process with that low delta parameter. So for 40 steps, you see something. We'll see something like the figure on the left, and for 4 steps, we'll see something like the path on the right. And as you can see, if we use the same random numbers, every method will follow the same pattern. That's exactly the idea. And then at final time, in this case 2, we'll compute this mean difference and the difference of the means. And yeah, basically we'll repeat that for every delta t. And I've done that for 100,000 of these paths. So I've generated 100,000 of these paths and then computed the weak and strong errors. So this is then what we get. So for the vanilla GAN and the constrained GAN, let's see. So let's unpack what we see here. The orange lines are the strong errors, and the blue lines are the weak errors. So the differences in the means at final time. And then what we see is that the Euler scheme, the strong error increases very rapidly with delta t. We know that, of course, if we take delta t large and the strong error in the discrete time scheme, and the weak error will go up. But the weak error of the Euler scheme and the weak error of the GAN and the is also at some point much lower already than the Euler scheme. So it's interesting to see when is the GAN outperforming the Euler scheme. That's basically what we're trying to see from this figure. And the strong error is very quickly outperforming the Euler scheme for both cases, and the weak error for some larger time steps. So this shows that both GANs are actually able to provide both a strong and a weak approximation. Although just as what we saw in the ECDF plots before, the constrained GAN is doing a better job in approximating the distribution than the vanilla GAN. So now you may wonder, if both can provide a strong approximation, then why did we need the constrained GAN in the first place, right? So the thing is that this is only a very special case. So I've tried it on GBM if the Feller condition was satisfied. So for one, if the delta parameter is such that we don't get this near atom at the origin, and for the case where we do get that atom near the origin. And in most cases, in many cases, the vanilla GAN did not find a strong approximation. So I have some, so we can understand that by looking at the map that that both neural networks have found. And what I've plotted here is the output of the neural network on the vertical axis and the input to the neural network, so the random sample that we've given to the neural network on the horizontal axis. So then we can visualize, if we fix the conditional parameters delta t and st, we can visualize which mapping it has learned. And then we see that indeed, as we saw in this figure, that both neural networks correspond to the same map, and both also correspond to the exact simulation scheme, the map that is implied by the exact simulation scheme. So indeed, in this case, we expect all solutions to be strong approximations. So I've shown it here for different delta t's. And you see that the curve sort of shifts with delta t. So here you see how the mapping is sensitive to delta t. But this is not the case in general. So there's many networks that I've trained during my thesis. And many of the examples where I trained the vanilla GAN produced not a strong solution. So to give an overview, I've made this slide. So on the left, in the first column, you see the result for GBM. So all these mappings roughly give an approximation to the conditional distribution, but they all correspond to very different maps in the plane of the output of the neural network and the random variable that we put in. Although you would, if you only look at the bottom histograms, you would say, oh, I found an approximation in distribution. But actually, you have not found a strong solution because all these maps correspond differently to a solution. So if you put in a random number, you may get out a different number than what the SDE prescribes, given that Brownian motion. So we get an approximation in distribution, but not pathwise. And to show that, I've actually shown examples of paths that you get with these different mappings. So on the left, you see that the mapping from the neural network is the mirror image of what it actually is supposed to be, and that corresponds to getting sort of the mirror image of your paths. So that's easy to see because, for example, take a very simple SDE. For example, dSd equals dW, so just a Brownian motion. A Brownian motion itself is a solution to an SDE, of course. And then you take minus W, which is also a solution. But it is not the strong solution because it's not equal pathwise. You'll get the mirror image, right? But it is equal in distribution by symmetry of the Brownian motion. So if you find a solution and you take minus, you define a new Brownian motion as minus W, you also find a solution. But that's basically the mirror image of that solution. And that's what you see actually happening in these neural networks as well, where the GAN's objective function is to minimize some divergence between distributions. So it doesn't care about whether it's found a strong solution or a weak solution. And that's basically what you see happening as well. But not only does it provide a sort of mirror image, it also sometimes produces a very strange mapping. So that's what you see on the middle and right figure, which are examples of the CIR process. So the histograms, from the histograms, you can't tell that these maps are so strange. But so although it's a close approximation in distribution, it's not a very parsimonious mapping to get an approximation in distribution. And these mappings would become very sensitive to noise. For example, take the rightmost column. Then if you are around the origin and you perturb the input slightly, then your output changes immediately by quite a bit, right? That's what you see in the right top right figure, for example. And that makes the GAN output very sensitive to perturbations, so to what is called attacks in the literature. And this is actually what happens with people building image generation algorithms as well. You perturb your input slightly and suddenly you no longer get cats but dogs, and sort of this kind of example. So that's actually a weak point of GANs, and it's interesting to see that we can also evaluate it in this way on simpler problems. So as a final result, I wanted to show you what actually makes the constrained GAN learn as opposed to the vanilla GAN. And because so far we've only looked at the generator output, but what's also interesting is to consider the discriminator output. So what I've plotted here is the discriminator output, which is a number between 0 and 1. And I've plotted it in this plane of where I made these plots about the mapping that the generator has learned. So I've superimposed both images. And what you see is that the discriminator has identified a region where it has produced a sort of band-like shape. And the value in that band is around 1/2. And like I mentioned in the beginning, if the value of the discriminator around an output is around 1/2, it means that it's not sure about whether it was real or fake. So whether it came from the generator or from the real data set. So every point that is found in that band, if the discriminator works correctly, should be that means that the generator has found a very close approximation to the exact solution, because it has successfully fooled the discriminator in that region. So, but any point outside of that band would be classified as fake. As you can see, is a sort of a blue ocean of values close to 0. And I've also superimposed the mapping from one of the vanilla GAN outputs, which are the blue dots. And there you see that these this discriminator would have classified almost all of them as coming from as being fake, so as not coming from the real data set. So this incentivizes the generator network through its gradient to put its samples closer to where the discriminator does not know whether it came from the real or fake data set. So the discriminator essentially identifies this map in the space of the solution with the random input Z. So it actually identifies this curve that I also showed at the top row in this image as well. So it identifies which map the generator should learn, and that's how the constrained GAN is different from the vanilla GAN. So yeah, let's take a step back and see what I've been doing. So there's now this model that can find a strong approximation to an SDE. If you can find your conditional distribution, you can find a training set. But it can be applied in a more general setting. So what I've been doing, I've been looking at Ito diffusions. So those are SDEs that don't depend on t, but only on the previous value and the time step delta t. So if you look at more general SDEs, you should also take into account the current time step, but that can just become an additional parameter into the model. And as well, you could look at the SDE parameters. So for GBM, you could look at the mean, the drift mu, and the volatility parameter. So instead of just learning one conditional distribution, you learn a whole family of distributions. So you basically learn the entire SDE family for a certain range of parameters. So this is a way you could extend the method to more general problems. And another thing is that we saw in the plots where I showed the weak and strong error that the GAN did not perform equally well for every delta t. But of course, we know that exact simulation does perform equally well for every delta t. So why is that? Well, that's because I'm not taking into account that in the training set, every subset with a different delta t has a different variance. So the subsets in the training set with low variance, they learn slower during the training phase than the samples with high variance. That's a property in general of neural networks, that the rate at which the weights update is proportional to the variance of the data set. That's why it's important to always normalize your data sets. One of the reasons why it's important to normalize your data set. So a more advanced pre-processing technique would take this into account, and I should basically scale with a different parameter proportional to delta t for each subclass of the data set. But the downside is that maybe you lose some information about how the output distribution should change. So that's a bit, I still have to think about how to do that. And yeah, there's some further optimization about the training process. There's different algorithms. There's a lot of GAN flavors that may produce better training, more robust and stable training. And we would need an extension to go to higher dimensions and non-Ito SDEs, some things like fractional Brownian motion or more exotic things like that. But basically, in conclusion, there is this GAN scheme that, that allows strong approximation of Ito SDEs. And we've learned that something about GANs in general is that if you look at the map, that they may be non-parsimonious and they may be sensitive to attacks, like small perturbations in the input. And we've related the input and output of the GAN to the ability to provide a strong approximation. And basically, yeah, as a takeaway is that this project for me has been also very interesting to think more about SDEs. What does it mean for a neural network to provide a strong approximation? That's basically been one of the central themes. And this project is sort of able to help us provide more insights into what would be the conditions for a neural network to provide a strong approximation. That you have to be mindful of the map and not just find the distribution. That's not enough. So with that, I hope you find this interesting. And with that, I'd like to close.
All right, thank you. That was very interesting. Are there any questions?
I have a question. You'll notice. So I wonder, you've discussed a lot about the weak versus strong approximation. I wonder in the finance context, where you've used these ideas, what are specific reasons to want a strong approximation rather than a weak approximation? Why is that important?
Yeah, that's a good question. So actually, there was a hint of this, I think, last week in Boris's presentation as well. So if you look at this figure again, so last week, I think we discussed some types of option contracts, where, so normally you would be interested in not just in the asset process itself, but you may be interested in some function of the asset process. So if that process is just defined at one time, so suppose that we are only interested in the value of an option contract, for example, at time t plus delta t, then we don't need strong approximations, because then you can just do your Monte Carlo simulation, compute the mean, and then your mean value will give you the value of the option contract. But suppose that your option contract depends not on one time, but is a function of several times in the future. Then it's important how these values relate to each other. And then you need the whole history of the path becomes relevant. So for those types of applications, then the strong solution is relevant. And an example is, of course, a Bermudan contract, where your Bermudan option, where your payoff is at several time steps. So your whole strategy depends on what the process does at several time steps in the future.
And wouldn't you want to look also at so for a weak approximation, it's a joint distribution over those different time points, or does that get too complicated? I mean, it becomes higher dimensional, of course.
You mean the joint distribution of what? Of the
of value at these different time points.
Ah, right. Yeah, maybe you could also look at the joint distribution, but I think in general it's very difficult to get analytic approximations of these things, right? I don't think that would necessarily help you more than if you start from I have these dynamics and I want to know the value at time t.
Okay, and so then a strong approximation would just be more convenient to achieve that.
Yeah, I think so. But I don't know if there are. I actually don't know if there are also schemes that make use of the joint approximation. But I can imagine that it's much more difficult in general to find that to find a closed form expression for these things.
Okay, thanks.
Anybody else?
Maybe a layman question, Jorino. So for the time integration of SDEs, you apply Euler-Maruyama. And for time integration, we know of ordinary differential equations, say initial value problems. There's a rich collection of methods. Euler-Maruyama is an extension of straightforward Euler, I think.
Yeah.
Is this rich collection which exists for ordinary differential equations, can it be carried over to SDEs? I know one other, the Milstein scheme or so.
Yeah, the answer is yes. So you can basically, all these explicit schemes like the Euler-Maruyama and Milstein schemes are basically different orders of the stochastic Taylor expansion that you can do. So where you truncate gives a different kind of scheme. So the Milstein scheme is basically the Euler scheme plus a correction coming from Ito's lemma, right? So then you get a higher order strong approximation. So I've actually used the Milstein scheme as well in my in some of my results. But you can also even define Runge-Kutta type implicit schemes. So that's possible. But then, yeah, so they may have more, they may have better stability properties, but they were not as relevant as an exploration for comparing a neural network to an existing data set. So indeed, for general SDEs, you may want to use such a scheme, but for these two SDEs, it was enough to just use Euler and Milstein.
Yeah.
So I have one question related to the previous one. So correct me if I'm wrong, but I don't think either of Euler-Maruyama or Milstein converges strongly for the CIR process.
So why do you think it does not convert for the CR? Yeah, so
yeah, it has to do with the square root term in the diffusion.
Yeah, that's, oh, I see what you mean. So that's yeah. So I'm actually using a modified version of the Euler and Milstein scheme. So I'm using a different version that always ensures that the values remain positive. So a truncated version of the Euler and Milstein schemes. But indeed, you're right. So there are quite a lot of papers about this. How should you do that accurately? And it very quickly gets messy because there's always these regions in which these methods can be shown to converge, but you can never say, oh, it converges for all possible cases. So you're right about that. Sure.
I have a question related to what Dan asked about strong converging. So what I get from your talk also is that if you compare the let's say the Euler scheme with the GAN, then you need to make sure that the random number generator is the same if you want to compare strong solutions, right?
Yeah, yeah.
So I'm wondering a bit, how much is that worth then if you go to a practical setting? Because it seems a bit like you have trained now the GAN to exactly reproduce those values of the random number generator. Is that the case, or?
No, I think that's a fair point. So if you look at this expression, this is basically how the training set is constructed. And then what you're saying is, well, then what's the added value if we already have to go through all this effort to construct this training set? So the thing is that equation 7, you can also replace the exact distribution. So suppose you don't know the exact conditional distribution, then you can still approximate it with some increasing variant of a CDF. And then you could basically, normally you don't have a way to, if you only have a discrete time scheme, to go from time 0 to time big T in a single step. But then you can use this algorithm to skip all the intermediate steps. So normally if you have an Euler scheme, for example, you need to compute every intermediate step. You just can't get around that. The added value would be that this random number generator gets there in a single step, and it can be faster in some applications. Does that make sense? Or
Yeah, that makes sense. But I'm wondering about, it seems like you have trained it for specific values that were the input to the random number generator, and you sort of need to fix that value again when you use that value again when you use your GAN.
No, because it can. So if you look at this, these mappings that it gives, it can also it also interpolates between these values. So if you would not sample exactly one of these training points, it will just find a value that is close on this curve. So if you use enough training data, then it can generalize, and you can actually sample using this network as well.
Okay, thanks.
Have you tried adding some memory to your GAN, or is that not relevant in this case?
That's a good question. So normally for financial time series, what people do is that you build a history. You look at a sort of rolling window of your, that's basically what you mean, I think, right, Wouter?
Yeah.
That's the you look at a sort of a rolling window of your solution. But for Ito SDEs, that doesn't make a lot of sense because they're Markov processes. So all that you need is the previous time step. So that's why this this is also how I set up the network.
Okay, I think my daughter's hungry. Sorry.
I've maybe last question, sort of more practically, what kind of software did you use, Jorino, to train these GANs, and how computationally expensive is it to train them?
So I used PyTorch to generate to basically make the GAN converge during the training set. So I use that framework. In terms of how expensive it is, so I've used, I found that 3 to 4 hidden layers with 100 or 200 neurons is enough to make this converge. But it takes a few minutes to train that on a GPU with a data set of 100,000 samples to give you an idea. So yeah, I don't know if that's exactly what you were looking for. Those are more like the specifics of the training.
Right. Well, yeah,
so
because I've heard that GANs can be are very expensive to train. So this is why I was wondering.
Yeah, but you're right about that. So they maybe need more data. So 100,000 is for these type of 1D applications, quite a lot of data. And of course, I also made it work with 10,000 data points, and then it also works relatively well. But you do still need a large amount of data, because the advantage of a GAN is that you don't need to specify some loss function. You just give it data and it will learn. But the downside is that you need a lot of it because it may be less efficient.
Thanks.
Anybody else have a last question for Jorino? Otherwise, I think it might be a good time to close. So thank you for attending. The next 3 speakers will all be external, I think. And the very first one will be Kelby. So most of you will remember her, and she will hold her talk next Thursday. And so hope to see you then, and have a nice evening. And thank you again, Jorino.
Goed gedaan, Jorino.
All right. Thank you all for coming, and see you next time.
Dankjewel.
Bye.
Goed gedaan.
Goed.
Right.
Doei doei.